with the imbalanced classes. Hopefully we'll be able to finish that off and start the multi-labeled lecture as well, so that we're at the right place for classes. Okay, so what are we going to cover today? Well, we're going to be talking about how we deal with training classifiers when we've got imbalanced data. So some of the data science students, that would be a good thing for you to pay particular attention to if you've got a imbalanced problem. So we're going to look at ways that we can affect the training. We can do and cover some data level algorithms. We're going to look at things called cost-sensitive methods, and then how we would design an ensemble to deal with imbalanced classes. So fundamentally, we've got this split between what's named algorithm-level approaches or data-level approaches. What do you think the difference between them would be? Not a trick question, I promise you. It might sound like one, but it's not. So what is the difference between this whole idea of algorithm level approach or data level approach? Any ideas? Don't worry if you get it wrong, that's fine. It's just what do you think it might be?
Probably specific set of rules.
Specific set of rules for what? The type of data or the type of algorithm. Okay, yeah, that's definitely one way to look at it, but what about those things?
Maybe just to do with like looking at the classifiers and looking at the data.
What do you mean by looking at?
The operating set of rules gets to do with more of the
changes the data and algorithm, changes the way we treat the data.
Okay, so yeah, you've actually hit the nail on the head. When we're talking about algorithm level approaches, we're talking about either using different algorithms or changing how the algorithm works. When we're talking about data level approaches, we're talking about somehow changing the data and use the traditional methods, but now with changed data. Okay, so let's start off looking at the training approaches, the algorithm level categories. So these are the different forms, the algorithm level ones. Effectively, we're saying we've got a set of algorithms, a group of them, that are specifically designed to work with imbalanced data. If you put it on a balanced problem, they would perform really badly. But put it in an imbalanced class problem, it does really well. Data level, we're talking about transforming the data from imbalanced to more balanced or to absolutely balanced. So we're changing the data and then we use the traditional algorithms that we've already studied. The cost-sensitive approach I started talking about lies somewhere in between the two. Okay? And what we're trying to do is saying, right, different types of misclassification cost us more. So remember the example we used 2 weeks ago before reading week? I know, all that time ago, we talked about having a classifier that was trained on a disease, and that only affected 1% of the population. So I write my classifier to just say, not infected. I'm right 99% of the time. Perfect. But I never find the disease, and everybody that gets the disease dies. In one way, I'm doing excellently. In another, I'm doing really badly. Yep. We said that using different metrics, like the F1 metric, will help us determine that situation. Now we're going one step further. Now we're saying that actually not finding the disease is worse than telling somebody they need to get a jab, an injection, even when they wouldn't have needed it anyway. Because the injection, like a vaccine, say, is not going to hurt that person, and they might not have needed it anyway. But that's fine. That's okay. We don't mind that. But we really mind not finding the people that are actually affected. So if we get a not infected person wrong, that costs us less than getting an infected person wrong. We could say, asking somebody that wasn't infected to have the shot, that costs us 1. But missing somebody that's infected costs us 100. And so the algorithm then balances that up based on trying to minimize this overall cost, based on all of the errors that could have come up. And the final category draws on the previous ones. So we use a combination of algorithm approaches, data approaches, and the cost-sensitive approach, all in an ensemble. So just like regular ensembles, the idea is that each one is strong in different areas. And so when you put them all together, you're going to end up with the best approach for everything. Okay? Now, let's focus on the data level approach. What could we do in order to take a fundamentally imbalanced problem and make it balanced? Well, there's various different things that we could do. The first one, and one of the easiest to understand, is something called random undersampling. Now, what we do is we take the class that we've got the most of and pick out a random number of them to match the minority class. So we've now got a 50-50 split. We pick any one of them at random. Okay? Now, the biggest problem with that is that, as we know from the training and testing protocols, when we're discarding data and we're not including it in our training, we could be throwing away very useful data about the overall distribution of the data. So, for example, this is the original view of the data. We've got far more black points than we do red points. So 2,000 black points, 50 red points. I'm going to randomly pick one set of 50 black ones to match the number I've got of red ones. And I end up with this plot. Now, what would you infer if you hadn't seen the first image? What shape does this data have? Well, if I was going to draw it, I would say that this data looks something like this. Yeah, it's an ellipse biased towards the bottom left-hand side of the axis, yes? Everyone agree? If I was going to do it this way, I'd end up with a big circle, wouldn't I? I've fundamentally lost all of the data about all of the image, the stuff that was over here. So if I train my classifier that way, everything in this area I'm going to get wrong, because I don't know about it. I don't know what data's there. So this is one of the quickest and easiest to understand methods that we could do. We just take a random number that matches our minority class from the majority one. Great, fine. Easy, no muss, no fuss. But it could be throwing away important and useful information about the data set. We could do this multiple times. And we could say that actually I'm going to take 10 random undersampling sessions and average it all over that. or I could include 10 copies of it, including the 50 bits, and that might be better.
What if you take more data from original?
But if I take more data from the original majority class, I'm maintaining the imbalance, aren't I? The whole point of selecting fewer from the majority class is to make it balanced. Yes. Oh, I thought the way the hand was moving, I thought that was a question. Sorry, it wasn't just that you had your hand like that. It was the way you twisted it. It was. Yeah, it was just sort of like. Okay, so this works, but it's potentially going to be worse overall. We're going to make more mistakes that way. How about we try the opposite? Let's try random oversampling. Now, what this means is that we're going to do the same sort of thing, but the opposite way around. So instead of throwing away any data from the majority class, we keep that as is. We're going to duplicate data from the minority class randomly to say that there's more with the same data. So it's exactly the same points, just stacked on top of each other. Same exact data, same exact distribution. It's just randomly duplicating it. Okay, not changing it in any way, just duplicating it. We've got more copies of the same data. So if I actually zoomed in on this part of the picture, we'd see that the dots are in exactly the same place. They're just thicker because it's the same data being plotted on top of each other over and over and over again. Yep. Now, what does this do? Well, we've got more data in exactly the same position for the smaller class. So any algorithm that is based on distributions of these data points and where they divide up, there's more points in a smaller amount of space. So we're going to overfit, aren't we? We're going to overfit to the minority class. Because there's now tens, hundreds, thousands of copies of the same data in the same place. That's going to bias all of the training, isn't it? So both of these are quick, relatively easy to understand, and they both have problems. They both suffer in one way or another. Now, depending on our problem, we might want to accept one or other of them. Yeah, in our disease problem, do we care that we don't necessarily pick up all of the different ways that people could be healthy? Do we care that all the different ways people can be healthy? No. We care about finding all the ones that are the disease. So we don't care if we've lost some of the data saying, actually, you can be 400 pounds, grossly diabetic, and still not have the disease. Yeah, we care about what makes you have the disease. In some problems, we don't necessarily know all of the situations where you do have the disease. Yep, think at the beginning of COVID. What were the main symptoms? We were told it was a temperature, a cough, and what was the other one? It was three things. It was a persistent cough, a high temperature, and a headache. Okay, and that was the only things. If you didn't have that, it wasn't COVID. What happened as the pandemic carried on? That list got longer and longer and longer and longer, didn't it? So if we'd oversampled it based on the first symptoms, yeah, we wouldn't pick up the fact that it changed and started going into your nose and things like that later on. We'd say, nope, that's not COVID. You have to have those three things. So we would have overfit. Yep. Okay, hang on a minute. I just used the same example, the same disease problem, and I've said that it's good in one way and it's not good enough. How does this work? Well, it all comes down to which things we want to have happen. Do we care that there were some people that were asymptomatic with COVID and they were still fine? Well, during lockdown, we don't care because they're not going anywhere. When lockdown finished, when we were all allowed out again, we very much cared because they were still infectious. Yeah. So a different part of the problem with COVID, this overfitting would have been fine, and we would have gone with it instead of the undersampling approach. Later on in the problem, our requirements have changed, and suddenly the problem that this method has isn't good enough anymore. We need to change our approach. Okay? Is there a better way? Is there a third way? You know that old saying, there's always a third way? Well, luckily, we do have a way. It's something called SMOTE, S-M-O-T-E, which stands for the Synthetic Minority Oversampling Technique. The T and E come from the technique. This is different. So instead of oversampling where we're duplicating the data and it's the same values of the same features over and over and over again, this basically generates new data that is similar to, but not exactly, the original data. Okay, so while the number of new objects that we've got hasn't been reached, so until we've got enough, pick an object from the minority class, we'll call that X, and then look for K nearest neighbours, the K ones that are nearest to it. Choose randomly one of those K neighbours. So pick one of those neighbours at complete random and draw a line in all of the feature space between them. Then generate a new point that sits halfway on that line. So if I pick that my blue point is my X, I want to find the three nearest objects. So that's going to be that one, and that one. All right, Peace, pick a number between 1 and 3. 2. Right, so that is object number 2. So I'm going to generate a new synthetic point that we haven't seen between, halfway in between X and neighbour number 2. Okay, but I still need to find another 50 odd objects. So I've got to repeat that process again. Let's pick this object. Okay, this is my new X. I find my 3 nearest neighbours. And now, let's see. Vera, pick a number between 1 and 3. 3. Okay. So I now generate another new point halfway in between my new X and neighbour number 3. If I keep doing this, over and over again, have a look at all the dots that I've drawn. They're roughly in exactly the same distribution as the original data, isn't it? They're all contained with the same distribution because they're halfway in between points that I've already got. I'm avoiding the overfitting because it's not the same data over and over again, it's new data. I'm not losing any information because I haven't thrown any structural information away from the majority class. I'm just balancing up the number of objects that I've got with new data from the minority class that looks the same. Yep. So let's now do it with, I believe I did it with 5. So let me get rid of my inkings. So 5 nearest neighbours. Okay. I pick one randomly. Let's say that line there, the black one. I generate a point on that line. Now I could do it halfway. I could do it randomly. Now what's the danger of me doing it all the time at halfway? Sorry? Combinatorial? Yes and no. Yes, it can be combinatorial because it could end up being the same one over again, but that's the reason why it's the problem, isn't it? Because if I do it exactly halfway all the time, I could end up doing the actual oversampling and duplicating the point again, couldn't I? Whereas if I pick a random length along that line, the chances that I pick exactly the same length multiple times is very, very low. Yep. So I add it at the random position, and I just keep repeating until I've got enough objects. I'm creating synthetic members of that minority class that are like the others, but are not the same as the others. Okay? Which means that my traditional algorithms and my traditional training approaches still work, because I've now got the same number of objects in each class. Yep. Yes, but we're doing it randomly within a constraint, aren't we? Because I'm not saying add a random position over here. Yeah, so the points are still within. If I draw an axis like that, that point is still within the distribution, isn't it? It's inside it. Yes, it's making it more dense than it was before, but it's not like I've just gone, you know what, I'm going to put a point over there. Completely outside of the realms of where this data was. It's similar to, but not the same as. That's why we call it synthetic. We're generating, we're creating this new data. Okay? What's the danger of a synthetic point? Good question. Nothing.
So we can use synthetic points.
Yeah, we can use the synthetic points as our x next time. What's the danger of using this synthetic data with the classifiers? Yep.
Can it ever not create points that are kind of underfit? As in creating points between two places that don't really exist for fitting actually.
No, because it's going to always have a convex shell, isn't it? It's going to have a convex hull, because the outer edge is always going to be the lines between the most distant points.
Mm-hmm.
So it's always going to be within that limit,
Okay.
in whatever dimensional space we're talking about here. So it's always going to be within the realms of the other data. It's never going to go, right, you need to put a point completely on the other side of the plot.
But if, like, in a two-dimensional case, you've got like a circle, and it fits between the circle, and it decides to fit. Oh, because you're doing k nearest neighbour, so it wouldn't do that.
Correct. It's going to be similar to the original point. Okay, so let's look at what this would to actually produce in the same way we did for the oversampling and the undersampling. So my original data point, okay, I've got 150 black points and I've got 50 red circles. That's my minority class. I'm going to now use Smote to generate 100 synthetic new points. has the red suddenly vastly shifted where it is in the graph? No. It's become more dense. Yeah, absolutely. There's more points there now. Has it changed the shape of the data? No. Has it changed where in the plot the data is? Not in general. Yes, in terms of individuals. So we actually end up with more description of that minority class that is more similar to the original than either undersampling or oversampling would have told us. Yep. Okay, so let's have a look at the maths of how we actually calculate this new point. So A is our original data point of all of the features, whatever dimensional data we're talking about. It's nice and easy on the board to do 2 dimensions, but it could be 178. Doesn't matter. Okay, so A is all of the dimensions of that feature X. Once we've picked one of the random data points of the neighbours, that's our B, and that's the equivalent description of what we're doing. Okay, we want to generate C. That's our new synthetic point. Okay, that's going to have the same number of features as both A and B have. So how do we work it out? Well, it's a very, very simple formula. C equals A plus rho times B minus A. What does this mean in non-mathematics speak? Okay, so we start with the original point, then we work out the difference between the original point and its neighbour. That's the B minus A part. So that tells us the differences in all the features. And then we apply this parameter rho, which is a multiplier between 0 and 1, which effectively says how far down the line joining A and B we want to be. So how much of that difference do we want to apply? If it's 1, that's the same as saying we want it to be B. If it's 0, 0 times anything is going to be 0, so it's going to be point A. If rho is 0.5, we add it in the middle of the line. Rho is picked randomly each time. So it's somewhere along that difference. So it might look scary maths, but actually it's not that difficult, is it? Okay? We've done it by hand in the previous modules, haven't we? Yes, we have. Don't shake your head at me, Vega. I taught you. I know you did it. We talked about Euclidean distance, didn't we? B minus A, that's Euclidean distance, isn't it? That's the differences in all of the things. All we haven't done is we haven't done the square root bit, have we? To work out the actual distance. Because we don't want the distance, we want the proportion of the differences. So actually we've done this all before. Yeah? How do you make the row random? You pick a random number. There's not some special algorithm you have to approach it because it's called row. You pick a random number between 0 and 1. Yep, that's it. There's no. I wish there was more fancy bits to it than that, but it's not. It's just pick a random number. Just like picking the random neighbour from the 5 possibles. Yep. So if we're doing this as a 2-dimensional problem, we've got our point A, which is at 5, 8, and we've got our position B, which is at 12, 4. Okay, so that's my my positions, my A and B. Now, my row I have picked randomly to be 0.3. Okay, so this becomes 5, 8, my original A, plus the difference between B and A. So that's basically taking away corresponding elements times by 0.3. So 12 minus 5 is our 7. And 4 minus 8 is minus 4. Now, I times this bit together first. So 0.3 times 7 is what? What's a third of 7? 2.1. What's a third of minus 4? 1 point. Minus 1.2? Yeah, that's good enough based on the numbers I put in there. So 5 plus 2.1 gives us our 7.1. And 8 plus minus 1.2 gives us our 6.8. So that tells us that C is going to be there. Now, even if I hadn't drawn the line in, and just put C in there without the line, we could actually put the line in and see that actually it does lay on that line. And if we do roughly the same distance again, we can see that it's roughly in thirds, isn't it? So it's roughly 0.3 along that line. So our answer is plausible, even if we weren't sure that mathematics was correct. But the answer, the maths is correct. Yep. Make sense to everybody? Okay. So that's where we've got the point. Good. Right. Now, time for you to do some work. Consider the data sets shown in the picture. Explain how you would augment the minority class to sample, make the sample balanced using smoked. Calculate the new point and plot it on the figure. So, what would we do here? What's the steps? Right, so how many more points do we need? 1. Okay, so our number that we need to generate is 1, and so we need to generate a red X somewhere. So what's our next step? Pick a point. Okay. Let's see. Oja, pick a number. 5, 6, or 7? 7. Okay. Now, because we've only got 2 other neighbours, we're going to have to use two nearest neighbour because we haven't got any more. So now, let's see. Who can I pick on? Sorry? If there was only 1, then we have to use 1 nearest neighbour, don't we? Yes, but I've only got 2 other neighbours that I can pick when 7 is used as my starting point. Yeah, you pick either of them. But we can't do 5 nearest neighbour because we haven't got 5 points, is what I'm saying. Well, 1 nearest neighbour says that there's going to be 1 that is closest. 2 nearest neighbour it's still the chance of 1 or the other. Yep. Now, in this case, I think I actually made it an equilateral triangle, so it doesn't really matter. But in a real data set, one of them is probably going to be closer than the other. So if you only do 1 nearest neighbour, there's no randomness in there, is there? It's always going to be that closest one. The reason that I'm saying that we have to use 2 nearest neighbour is we should use 5 or a bigger number, but we've only got 2 other points. So we can't pick the nearest 5 because there's only 2. Okay? So, Oja picks 7. Ernest, 5 or 6? 5. Okay. So we are drawing a point somewhere on that line. Right, let's see. Sabir, are you here? Yeah. A random decimal number between 0 and 1. 0.4. Okay. So our row is 0.4. Right. Work out where that new synthetic point is going to be. Generated by Smote. Will lie. Okay, so it's going to be somewhere in that yellow triangle. Okay?
Yeah.
Good. Right. So let's move on to the cost-sensitive methods. So for cost-sensitive training, we're basically going to apply weights to the type 1 and type 2 errors of our confusion matrix. What we're saying is that actually the cost of putting a what for this cell, the false negative, which type error is this? Type 2 error? Type 1? Who's right? Type 2. So the cost for the type 2 error is going to be 5. The cost for the type 1 error is going to be 1. So what we effectively say is however many false negatives we get, times that number by 5. And work out the normal metrics. We're making it 5 times more costly for any point to be put in that cell of the confusion matrix. Okay? So, if I was to do this, this is my loss matrix. I'm saying there's 0 loss if I get it right. A loss for a false positive is 1. And a loss for the false negative is 5. Hang on, why is that? That's the wrong way round. That's the wrong way round. Hang on, is that because I phrased it differently? Ah, labeling the minority class as the majority is 5 times more costly. I phrased it slightly differently. So that means that if I get a majority class labeled as the minority class, that one, that's 5 times more damaging than that one. So I take the number of errors in that and times it by the cost. 2 times 5 plus 8 times 1. So the cost of this particular classification is 18. So therefore, we can assign weights to the objects equal to the cost of the misclassification. So 1 for all the objects in the minority class, the majority class. I can't even read my own slides. So 1 for the objects in the majority class, the minus, the black, and 5 for the objects in the majority class. Then we can use a classifier that actually understands object weights, like an SVM classifier, a support vector machine, whose algorithm already builds in these object weights, how important they are. Now, we haven't seen it in the way that we've used SVM in the past, but this algorithm does allow us to have weights. So what does that actually do? Well, without the weights, SVM would draw a classification region like this. we've got the red dotted outline of where the actual hyperplane that separates these classes are. When I add in the weights, it effectively makes the points bigger. And do you remember what happens with SVM? It's a largest margin algorithm to split the points. But when I make the points bigger, they take up more of that space, don't they? So the difference is going to be smaller. So it's going to find a different border where there is more space. And that alters the classification region. So effectively, it's getting the minority class more right at the cost of mislabeling 3 of the majority class compared to the previous one where it got the majority class perfectly right, but we missed a minority object. Yep, that's the minority object that got misclassified. And when we do the weights, that got correctly classified, but the other objects, the other black ones, didn't. But that's fine because we've said it's okay or more okay to misclassify the black than it is to get the white wrong. Now we used that as a basis for an example 2 weeks ago, didn't we? About prisoners. Yeah, we as a society have decided it's better to let a guilty person go than to convict and put in prison somebody that was innocent. Yeah, we've said it's more costly to convict an innocent person than it is to free a guilty one. That's exactly what we've done here using machine learning. Okay? Now, I was going to ask you a question about that, but given the time is moving on, I'm going to skip that one. When I put the slides up, you're welcome to do that as homework. So, let's move on to the final portion, the ensembles for imbalanced data. How can we generate an ensemble? Could you ask a question about that one? Yes. Is it always 1 and 5? Absolutely not. It can be whatever the problem dictates. It could be 10 and 1. It could be 8 and 4. It could be 10 and 100. It could be 1 and 10. It's just the relative undesirability of one of the errors. Yep. You'd think that, wasn't it? That's because of the way I phrased things. So the loss matrix is the opposite way around. Because what we've said is labeling the minority class as the majority class is 5 times more costly. Now what's confused everybody is I've not drawn this confusion matrix the right way up, have I? What do we say about confusion matrices? Assigned is meant to be the columns. Yep. So assigned is meant to be up here and true is meant to be there. That's why it's the other way around. I know. But what's this a demonstration of? Assumptions. We do say it does say assigned, doesn't it? It threw me the first time. That's why I had to go back and check. Yep. Labeling the minority class, the plus, as negative is 5 times as costly. So this time the assigned is in the right place. Okay. Sorry? But I've been nasty, haven't I? Is this a confusion matrix? I've deliberately drawn it the other way round for a reason. The loss matrix isn't drawn the same way round so that we don't confuse it with a confusion matrix. Sorry? I'd like to say yes, but unfortunately this is something that we've done as a discipline to try and separate a loss matrix and a confusion matrix because they look, without titles, exactly the same. We know by convention for confusion matrices the assigned are the columns. Yep. By convention, a loss matrix assigned are the rows. So that means they flip over, don't they? Or one of them at least flips over. So that's why we get 2 times 5. Notice it's still the same the same combination, assigned minus true plus. So 5 times 2, and the opposite way round is 8 times 1. Okay? Now, that might seem like a trick. That might seem like teacher being nasty. Why didn't I just call your attention to that the first time I went through it? Because that's exactly what's going to happen the next time you look at these things. Okay? You're going to go, oh yeah, it looks like a confusion matrix. Assigned must be the columns. Because it might not have a big heading on it that says, this is a loss matrix. Okay? So I've shown you how easy it is to confuse these things. When we're dealing with this cost-based problem, we need both a confusion matrix, which will be organized the way that we know and have been taught to be organized, and a loss matrix where it will be flipped over, and the assigned is always the rows. We will also see that getting it right is always a 0. Now, it's not necessarily going to be drawn in as a 0. It could be left blank. Why is that, though? Well, we always multiply that by the number in that cell of the confusion matrix. Yep. But it's not a problem. It's not a loss. It's not an error to get it right. So 0 times doesn't add into our cost. Yep. No, because it's not a cost of getting it wrong. We're interested here in making sure that we're getting the things more right than wrong. We're concerned with not the bits that we got right, we're concerned with how wrong we got it. And we're saying that actually the different errors are more or less costly. Okay? Now what happens when the cost is the same? So instead of being 5, this is 1. What happens? Well, we'd do that anyway, wouldn't we? It increases? No, it would actually go down, wouldn't it? Well, if I say that actually type 1 and type 2 errors are equally costly, they're equally problematic, not that one type is better than the other, what happens? Sorry? They're the same loss, or it's exactly the same classification problem we've seen before. Okay, so it only matters when the two types of error have different costs. Yeah, if they are both 1 or both 5 or both 50,000, it's exactly the same as just doing normal classification and the normal metrics. No, it's nothing to do with whether it's balanced or not. It's whether or not it's costly. Okay, because we could be using smote to make it balanced. But getting one of them wrong is still worse than the other in this particular example. If they're the same, it's just a regular classification problem. Because the multipliers there are 1, aren't they? So it only matters when the two bits are different. Okay, but make sure that we're paying attention that we're talking about a loss matrix or a confusion matrix, because it changes how they're represented.
The costs are the same. There's no need for a loss matrix.
Not really, no.
No,
No.
I don't know what no means.
What do you mean?
It's confusing me. Means you use the normal.
It just means the normal. We apply the normal metrics. Yeah. It's just a normal classification problem. We don't have to worry about having costs of weights and things like that. If they're weighted the same, they're weighted the same. Okay? It's only when they're not the same.
So for a particular data, I can choose 5 and 1, and that person can
Not for a particular data, for a particular problem. Okay? You could use the same data to solve different problems and they would have different costs. Yeah? If I take my example of punishment, yeah? I could say that actually the cost of me getting the wrong student to talk to about cheating, if I'm just talking to them, would be the same. If I talk to somebody about don't cheat and they didn't actually cheat, there's no harm. If I expel you because I think you've cheated and I get it wrong, that's very dangerous, isn't it? Yep. So I'm using the same data, whether or not you cheated, but I'm solving two different problems, and therefore the cost of making mistakes changes. Yep. Similarly, like we started with the disease, giving the vaccine to somebody that doesn't have the disease is not going to hurt anyone. But missing people that need the vaccine and we don't give it to, that's a big problem, isn't it? So there would be different costs. Summarily executing people that have the disease, we have to be bloody well sure they've got the disease before we start chopping people's heads off. Yeah. If it was just a case of go and stand over in the corner, would I be quite so worried? No. Killing people a little bit more drastic than putting them in the corner. Okay? Does that answer most of your question? Okay, all right. What's the real question then?
So she or you can choose 5 and 1.
Yes.
And I can come and choose maybe 8 and 1 or 8
Yeah.
and 2 or anything.
It's just relative in this problem that this is 5 times worse than the others. It could be 10 times worse. It could be that actually you put 3 of you together and you argue whether it's 5, 8 or 10 and you settle on somewhere in the middle. 6. Yep. Okay. Right, so let's go back to the final portion, classifier ensembles for imbalanced data. Right, so random balance ensembles is based on bagging that we've already seen. So we take L independent bootstrap samples of the dead, of the Z, not the dead. It's Peace talking about confusing people. Taking L bootstrap samples of Z with a random proportion of the classes undersampled or smoted. Okay, so we've done either the undersampling or smoting, and we take the independent samples. We train the classifiers on each one, so we've got L classifiers now. And for any given object X, we calculate the class label that each of the L classifiers would give us. This is exactly the same as bagging entirely at the moment. And we use the majority vote to combine it and assign a single class label to that object X. So each time we are randomly choosing more or less of that balanced class. Well, what's this? This sounds exactly like bagging, isn't it? Because, well, wait, it's not bagging, is it? It's actually more like boosting, isn't it? Because in subsequent samples, in boosting, we get the class that we got wrong more and more represented, don't we? So it's kind of like a combination of the both, because we're taking a proportion of the smaller class, bigger or smaller, to train a new classifier. So actually now we're solving both of those problems that we had for the different methods at data level in one go, aren't we? We're saying that actually we're only taking a proportion of all of the data anyway in each time. So we're ignoring some of the structural data in one classifier, but we're including it in another. And if we make enough L, if L is big enough, we are going to have a good representation of the whole thing, aren't we? Just like if we were to do a Monte Carlo experiment. Yeah? We take a random point and we put it into an equation and we work out where the answer is. We could work out the proportion of the area of a circle, for example, by deciding whether or not it falls inside a circle or not. We don't have to actually do the pi r cubed. Is pi r cubed? No, 2 pi r for an area. Pi r squared. Yes, pi r squared, sorry. I've gone through every formula of a circle and got the wrong one. Stop confusing me! No, that was just me getting it wrong. If we pick enough random points, we can say, right, so the overall area was the box that went round the circle, and there were this many inside and this many outside, so it's going to be that proportion of the area of the box. And working out the area of a box is far easier than working out pi r squared, isn't it? If you haven't got a calculator, that is. So we've got different proportions of each class in each classifier. So we're solving the whole thing in one go by effectively solving different classification problems each time based on the original. We're taking slices of the original data problem and doing one classifier on each. Now we could get really unlucky and all L are focused in one area of the data. But if our L is big enough, the chances of that happening is very small. Okay?
The minority class
Yes.
can be used that way without being smoothed.
We can smote it, or we can undersample the majority class. We're taking random amounts of both of them. So it has to be balanced, doesn't it? Because I can't have 0.8 of something that doesn't balance. Okay? Right. we really need to move on to the next lecture. I'm going to give you 5 minutes worth of break in between.